circuits. This says resistive inductive, but what is the symbol for inductance? L, that's right. So these are RL circuits. So whenever we abbreviate this, write RL. Okay, relationship of resistance and inductance to alternating current series circuits. Now, I've told you about our friend Eli the Iceman, right? Okay, so we know that inductance, what leads what? What do we know? Eli. EMF leads I. So voltage leads current, right? Voltage before current. So that's an easy way to remember. And in capacitance, the Iceman, ICE, I before E. So current before voltage. So define power factor. Power factor has a lot of definitions. And one of them is the true power over the apparent power, which is the system efficiency of the circuit. That's the system efficiency of the circuit. Because how much power are we putting out from how much input power? That's the definition of efficiency, right? And that power factor is always the cosine of the phase angle that is formed by the resistance to the total impedance, which is the same sides of the triangle as the true power to the apparent power, the side adjacent compared to the hypotenuse. That's the cosine, right? So the cosine turned into a percentage is the power factor. Write that down. Cosine turned into a percentage. How do we turn a decimal number into a percentage? Multiply times 100. So if we have 0.888, we know that's 88.88%, right? Okay, so we're going to calculate voltages, current, apparent resistance, inductive reactance, and power factor in an RL series. That's true. We're going to do that today, no doubt about that. And we're going to discuss vectors. What's a vector? Okay, you know that when we get any angle and it has a certain length, that's a vector. Okay, and the reason that comes up is because later we're going to add two different kinds of vectors, and really that's not a big. The way we're going to do it is nice and simple. Just remember to follow the steps. You won't get lost. Okay, don't try and overthink it. Just follow the steps. Okay, we're going to plot electrical quantities using triangles. Vectors, okay, that's true, but maybe a more difficult sounding way of talking about it. And it's really simple, so we really don't need to get all crazy about it. Okay, resistive inductive series circuits. So a series circuit with an inductor and a resistor, the voltage and current will be out of phase by some amount between 0 and 90 degrees. 0 is completely in phase, 90 degrees is completely out of phase, right? Pure inductive reactance would be 90 degrees out of phase from the applied power. So that's not a big. Let's go to the next thing. And by the way, this is what a motor looks like if you look at the idea of what it is. The resistance of the pure winding, the pure DC resistance of the winding is its resistive value, right? And it's got a pure inductive value. And you know that no winding is purely resistive or purely inductive. It's a combination of the two, and we know that we end up with triangles, right? Okay, so in this case, we've got a resistance of 30 and an X sub L of 40. And so we're going to have a triangle. Let's go down to the next slide. And we're going to say that we have 240 volts. And I want you to remember, what formula are they using to find this thing down here, the impedance? Pythagorean theorem. Stop that. Don't do that. Don't ever do that. Because what we're going to do is what I call simultaneous priming. We might find the resistance and the inductance. We're just told the resistance and the inductance of this motor, right? And we have a supplied voltage. Stop. That's enough information. Now, how do we find the power, the apparent power and the true power? Well, we can multiply the applied voltage and the applied current, and that gives us the apparent power, right? And the true power, the work being done, is some percentage of that. And guess where that percentage comes from? Go get the phase angle of that first triangle, because both the angles are the same angle. So for that same circuit, that same motor, we're going to have the same triangle. We said that we had, just in case you're wondering, we said that we had 40 ohms of X sub L, right? And we said we had 30 ohms of resistance, right? Now, they're going to do it by Pythagorean theorem. But let me tell you now why we don't want to do that. Nope. Sure enough, we're going to make a new slide. Okay? Insert. Where's slides? Are they not in the slide thing? Slideshow. I gotta go home. Thank you very much. Okay. Now, I want a new slide, but I want it to be a duplicate slide. Okay? Is that all right? That works. So now we have this one, where we have the original. Have I done this correctly? So unlikely, you know. So, because I'm going to write all over this second one. All right? So we have our original triangle here, and then we have the original resistance, which we can read with a meter, right? And did you know that your meter can read inductive reactance? Or can it? Or maybe we can infer it. Okay, because what is our supply voltage? We said this thing had 240 volts. Where did that say that? 240. Good deal. Okay, so let's go back and put our PEIR, or Z in this case, and we have 240 volts, right? Now, we don't know what this is yet, because Z is this thing right here. Now, they say it's 50 ohms. We're going to check that, because we're going to find it by the angle instead of Pythagorean theorem. I'll show you in a minute why we're going to do that. Okay, so what function do we have if I'm looking at the side opposite and the side adjacent? I've got the tangent, so I want to find the angle. So everybody pull out your handy-dandy PI30X2S. Let me hit pause while you do that. Okay, so if we take our calculators out and we hit second function tangent 40 divided by 30 and hit enter, we'll find that we have a 53.1 degree angle, right? Now we want the angle because we want to do a different function to find something we can plug in and get our, what are we looking for? Hypotenuse. So sine and cosine both have that, right? But we like the cosine because that's the power factor, right? So now we're going to hit cosine, second function answer. In other words, give me the cosine of the last thing I found, which is 53.1 and all those other number of degrees. Now we're using the whole long number, right? Now hit enter. We find that the cosine of this angle is what? 0.6, right? 6 even. Everybody agree with that? What a coincidence. I wonder why that, we come up with that before. I wonder how that happened. So anyway, now that is, what is the cosine? Oh hell, another hour, right? Everybody agree with that? Okay, so what do we have? Do we have the adjacent? We do. 30 divided by the hypotenuse. So now we've got a 0.6 is equal to 30 divided by h. I don't like the way that's written. You know what I'm going to do, right? We've done this enough times that you're going to say that we're going to take and this, and we're going to exchange them. So we have 30 divided by 0.6 is equal to h. And all we did was exchange these two, right? Everybody see that? Okay. If we do it by multiplying both sides by h, divided both sides by 0.6, we'll come up with the same thing. It's just as a quicker step, right? If you know the steps, we can make quicker progress, right? So shortcut, shortcut, shortcut. Okay, so now 30 divided by 0.6. What's in your calculator right now? 0.6, right? Now the magic of this calculator is it doesn't care which order you put it in, right? So now we're going to put in 30, divided by second function answer. The last thing we found was 0.6. Hit enter, and we find our hypotenuse is 50. Or did we find 49.9999? 50 even. It's a miracle, I tell you. Our pure functional magic is working. Now, why do we want to do this with a triangle? Because that was so much harder than doing the Pythagorean theorem, right? Everybody agree with that? Well, we're going to forget about Pythagoras and his darn theorem. We don't even want to know him anymore. Sorry, Pythagoras, stay on outside. We don't need you. Don't want you. Don't like you. Because let me tell you why. We're going to take a new triangle. So we're going to look at this thing, and we had P, E, I, and Z, and our Z is 50 ohms. We know that, right? And our voltage was 240 volts. Okay, so now let's divide 240 by 50. Alrighty then. It just wants to screw with me today. I can understand that though. So now we have 4.8 in our calculators, right? Now we want the apparent power. What power are we putting into this circuit? It's just voltage times the current. So we got 4.8. Let's multiply times. So just hit times 240 equals. Gives us a number. What is it? And is that watts? Trying to scare me. It's working. 1152 VA. So what do we do with that information? That's our apparent power. What angle is this right here? 53.1 degrees. Okay. If that angle is 53.1 degrees, what is the cosine of that angle? Wait a minute, didn't we find that before? Is the cosine of the same angle still 0.6? Amazing, I tell you. So the cosine is still cosine of theta equal 0.6 is equal to, oh hell, another hour. Well, this time we have the H. We have 1152. Look at this. We only have one variable missing. The side adjacent, which we'd kind of like to know. We get rid of that by multiplying both sides by 1152. So 0.6 times 1152. Can you see why this is called the power factor now? The cosine of this times the apparent power gives us the true power. It's the power factor. Now you see why though, right? So 1152, we've got, what's in our calculator right now? 1152 times 0.6. And, say again? 691. Is that VAs? That's watts. That's a real live amount of work we're getting out of this circuit. We're getting 691 watts of work out of the circuit. Okay? Now we can find the reactive power, which is the thing over here. The X sub L. The X sub L is this over here, and the result of that X sub L is our volt amps reactive. Now, we find that with a different formula. We do that with the sine, okay? The sine of theta is what? Oh, hell, right? This opposite is what we're looking for. What is the side opposite? Hypotenuse, we already know, right? So let's go back and hit, just finally, we're going to hit clear. Okay, have we hit clear so far? Not until we started, right? Now hit clear, just this once. Now hit sine, 53.1, enter. Okay, sine of theta. Now that's the sine of this angle and the sine of this angle, right? Same angle, so same sine. So sine of theta is what? 7,996. In other words, 0.8. Okay. Well, let's go with 7996. I can go with that. That's okay. That doesn't bother me. So that's equal to, oh hell. Everybody see that? Now, if 0.77996 is equal to O over H, don't we know one of those? We know the H already. Everybody see that? The hypotenuse we already know. So let's plug that in. We're going to say that the side opposite is equal to, or the sine is equal to 0.7996 is equal to O divided by 1152. What are we going to do to get O all by itself? We're just going to multiply both sides by 1152, right? So we multiply the sine of the angle, which is 0.7996 times 1152. What's in our calculator right now? 0.7996, and that whole long number, right? Times 1152, and that will tell us our bars. So let's multiply that out, find out how many bars we have. How many? 921? 0.2. So now we found out everything we can about this circuit, right? We know how many bars are being created because the inductive reactance, and later, not too much later, we're going to figure out how to get rid of all these bars and how to get rid of that X sub L. All right? But this is the essence of what we want to do here. So let's go to the next slide and see what this is about. Okay, oh, that's just working out the problem we just worked out. So just going to do a Pythagorean theorem, which we would never do. Okay. What are we doing here? 240, 50, 4.8. Oh, it found the voltage drop. What we did not find is we could have done another triangle, and we could have found our voltage drop across the resistor. Okay, and we could have found the voltage drop across the inductor. And that doesn't add up to the supply voltage, does it? Why is that? Because it's AC, it doesn't add up. It's got to be a triangle. Okay? So what would we do? We wouldn't do it their way. We would take, what was our angle? 53.1 degrees. Come back. Come on back, please. 53.1 degrees, right? And what is our supply voltage? We know that's 240 volts. That's our total voltage, right? It can't get any more than that, right? So what was our cosine? Cosine of theta, still 0.6, no matter which kind of triangle, how big that triangle is, the cosine of that angle is still going to be the cosine of that angle, right? And that's equal to, oh hell, another hour. Don't we know one of those? We know the hypotenuse, so let's get rid of that, put in 240. So we know A over 240 is equal to 0.6, so we'll multiply both sides by 240. So if we just multiply 0.6 times 240, we find the sag adjacent. What is it? 100? Oh, shocking! We found it a different way. And the same thing with the side opposite. We would use the sine, multiply the sine of the angle times the hypotenuse, and we find, what a surprise, 192 volts. So I want you to notice something. Add up 192 and 144, you get way more than 240 volts, don't you? How is that physically possible? How is that possible to have more volts than you were supplied when they're across the resistor and the inductor? Any ideas? No ideas at all. Because they do not happen at the same time. The inductance and the resistance are out of phase, remember? They're not happening. Remember the wave going up and coming back down and then going back up? Okay, that's what the power is doing. But remember that the resistance and the inductance are out of phase around 90 degrees. How much is this one out of phase? 53.1 degrees. And that means that there's a shift between the supplied voltage and the inductive voltage. There's a time shift. There's a time lapse in between. So they're happening at different times. You have part of this wave and part of this wave, and some of them, again, they don't add up to the half of the wave or the full wave or anything. It just doesn't work. Not happening. So don't worry about it not adding up. Just remember that it's the result of this time shift of the phase angle of the relationship between the inductance and the resistance. Pretty cool, huh? Okay, so we have a different way of finding it than this book, and we're going to keep doing it this way because once we have the angle, we can find everything with our method. With their method, everything's a struggle. Take my word on this. It's much harder because if you find the stuff from the first one, you don't have the angle for the second one, so you got to start if you don't have two sides, you're kind of screwed, right? So there we go. So that's why we do it by this method. And let's see. We have, is that our same one? So here we're going to find our powers. I'm not even going to get into that. Remember the applied power, the true power, and the apparent power? Yes, that's true. Watts divided by VA is going to be the power factor every time. Okay, I think that's everything our slideshows wants to tell us, even though it looks like they want to talk a lot more. But it really doesn't have anything else to say, except do it Mr. Rogers' way. It's much easier. Okay? It's nice and easy. Once you get the angle from any one triangle, you get all three triangles. Voltage, power, resistance. Okay? What kind of circuit has it got to be to have a voltage triangle? Series circuit. So when we do parallel circuits, will we have a voltage triangle? No, the voltage is the same everywhere. You got a flat triangle. Flat triangles are called straight lines. Straight lines. Okay? So that doesn't work out. What we have in that is a current triangle. Okay. That's the lecture today. Sorry. That's it, folks.